Mhm. 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 Hello everybody, welcome to our channel. Here we plan to explore some deep ideas that shape our universe. From the smallest particle inside the atom to the vast structure of cosmos, physics reveals patterns that are both beautiful and profound. Here we plan to discuss fascinating topics in fractal geometry, particle physics, nuclear physics, mathematical physics, quantum optics, etc., making complex ideas clear and engaging. Whether you are a student, educator, researcher, or simply curious about universe, this channel is a place to explore the science behind the reality. Welcome again to the channel The Physics Mind, where science meets wonder. In this series, we will explore hidden mathematics behind fractals, their connection to chaos, and how they shape the universe around us. If you are curious about the deep patterns of nature, you are in the right place. Let us begin our journey into the infinite world of fractals. Join us as we discover the hidden patterns. So the outline will be as shown below. We will start with a short introduction. We'll go through early history. We will know the meaning and basic definition of fractals. We'll also discuss the origin of the concept of fractals. What are the key characteristics of fractals? Self-similarity, the scale invariance, integral dimension, fractal dimension. At one time, it was believed that the geometry of nature is centered around simple figures like lines, circles, spheres, polygons, conic sections, quadratic surfaces, etc. But in nature, there are manifold patterns which are very complicated and irregular. There is no similar geometric configuration in classical geometry that can be used to model them. How mountains and trees can be geometrically constructed using familiar objects from classical geometry. How can we describe the intricate tree-like structure of lungs and kidneys in the human body? What is the mathematics behind the turbulent weather or cascading waterfalls? What is the mathematical model for the onset of panics in the financial markets or even social behavior? What is the mathematics behind the heart and brain waves as seen in electrocardiograms? No one knew the answer till Benoit B. Mandelbrot and his collaborators showed that this can, of course, be done by means of fractals. Nowadays, fractals and mathematical chaos are mathematical tools for analyzing many of these questions. The term fractal applies to a particular static geometric configuration, such as image of a waterfall. Chaos is a dynamical term used in describing such phenomena as turbulent weather. Several geometric objects like Cantor set, Sierpinski triangle, Koch snowflake, etc. were known which have fractional dimensions in the sense of Hausdorff. Benoit B. Mandelbrot named them fractals. He developed a coherent theory of fractal in his book Fractal Geometry of Nature. Fractals started appearing in mathematical literature over 100 years ago. Like many other mathematical innovations, fractals were met with distaste. One famous mathematician, Charles Hermite, labeled them as monsters, and considered them to be of interest only to researchers who indulge in mathematical oddities and not to real world scientists. As a result of the efforts of Benoit B. Mandelbrot, fractal geometry has become a respectable applied science that offers research possibilities in any number of applications like medicine, soil mechanics, seismology, geology, in pure mathematics, in electronics and communication as well. What are the key characteristics of fractals? A fractal often has following features. It has fine structure at arbitrary small scale. It is too irregular to easily described in traditional Euclidean geometric language. It is self-similar. Self-similarity is seen if you look at the picture of a tree. In most of natural objects, there is a repetition of patterns at various scales. A tree has branches. The branches have smaller branches and so on and so forth. The pattern of branching is repeated every time, each time with a smaller scale. The same is true of mountains. Any part of a picture of mountain looks like a mountain. There is a near repetition of basic shape at ever smaller scale. This is the self-similarity property, that is characteristic property of fractals. The relation between fractional dimension and self-similarity is that the simplest way to create a set with a fractional dimension is through self-similarity. If a part of a fractal is enlarged, that is, unit of measurement is reduced, then it closely resembles the original of which it is a part. It has the same fractional dimension as the original. The same process may be repeated by this part and the same result is observed. This process can continue indefinitely. Integral dimensions. In order to understand the fractional dimensions, so let us first go through the definition of integral dimension. Physical objects are generally specified as 1, 2 or 3 dimensional, or they are dimensionless, that is of 0 dimension. This is because our sense of physical perception is limited, although our mental perception has no such limit. All orthogonal curvilinear coordinate systems have only 3 dimensions. Physical events, on the other hand, can have more than 3 dimensions. For example, force has 4 dimensions and energy has 5 dimensions. We all know force has got the dimension ml t to the power minus 2 and energy is having dimension ml square t to the power minus 2. Dimensions of physical objects are, for convenience, described in integral numbers. But not all objects in nature can be tied down to this simplified system of description. Now, there are surfaces of mountains, shapes of clouds, lightning bolts, coastal geomorphology of any landmass, and various vegetables that are some of the examples of natural objects that integral dimensions cannot describe. Mandelbrot used the word fractal to describe the characteristics of such objects and events that have fractional dimensions. While objects and events having integral dimensions have a smooth contours, The fractal dimension denotes the roughness of the object or the event and can be used as a measure of the same. So let us consider a line segment. We know that it is having dimension 1. So consider a line segment of unit length. Suppose the line segment is divided into n equal parts. Each smaller part can be deduced from the original segment by a similarity ratio R. The similarity ratio R is 1 by n, or we can write nr is equal to 1 or nr to the power 1 is equal to 1. Just notice that we have written the subscript 1 over r. In the figure shown, it is seen that capital N is 4. The line segment has been divided into 4 equal parts so that r is equal to 1 by 4 and nr is equal to 1 so that the value of d is written as 1. Similarity ratio R can be thought of as the ratio of the length of a smaller line segment to the length of the original line segment. Let us take the case of a square. If a square region in the plane has its sides scaled by a factor r into n equal subsquares, then the relation between n and r becomes nr square equal to 1. It is clearly shown in the figure. Here we are having a square region that has been divided into 16 equal subsquares so that r is equal to 1 by 4 and nr square gives you 1. Similarly, if a cube has its sides scaled by a factor r into n equal subcubes, then the relation between n and r becomes nr to the power 3 is equal to 1. So here we see that the cube has been divided into 64 equal parts and the r is 1 by 4 so that nr cube becomes equal to 1. The interesting thing here is that the dimension d of the object shows up as an exponent of r in the relation between n, which is the number of equal subunits, and the similarity ratio or scaling ratio r, so that nr to the power d is equal to 1. The value of d in case of line segment was 1. For a square region it was 2, and for a cube the value of d was 3. So the configuration line, square and cube have integer dimensions d of 1, 2 and 3 respectively. The explicit form for d in terms of n and r is found by taking logarithm of both sides of equation 1. So taking logarithm of both sides in the equation, we get log n plus d log r equal to 0. This gives d is equal to minus log n by log r, or d is equal to log n by log 1 by r. Here it is interesting to note that the value of the dimension d is independent of the base of the logarithm. We can, however, imagine a situation in which there is a distribution of points for which the parameter d, which we call dimension, turns out to be a fraction. We call such distribution of points as fractals. In what follows, In the next video, we will learn about the fractal dimension through well-known examples so that it could be understood more easily. Thanks for the patient listening.